Okay, so can you see my screen now?
Yep, it's
Yeah.
there. It's in regular. It's not in presentation mode yet, but it's up.
Yeah, let me put, okay,
There we go.
presentation, yeah.
Okay.
Yeah.
So for those of you joining us, it's the top of the hour. We're going to wait another minute or two to get started. For people who will ask, yes, this is being recorded, and we will make sure that the recording is up on our iGuide website as soon as the recording is processed. My name is Diana Sinton. I am a senior research fellow with UCGIS, the University Consortium for Geographic Information Science. And we're here today as part of our presentation series to hear from one of the summer school teams from 2024 that worked for iGuide. iGuide is the Institute for Geospatial Understanding through an Integrative Discovery Environment. And I contribute to iGuide as part of its education team and its knowledge transfer and evaluation team. And we're really glad to hear from this group today on their work with machine learning and remote sensing and some surface water. So I am going to turn it over to them. We will have time at the end for questions. So thanks very much, everyone. And also I'll share a link to our other upcoming topics in our virtual consulting office sessions. So Mariam and Nitesh, it's all yours.
Thank you so much, Diana. Hi, everyone. I'm so happy to be here today and talk about one of my greatest experiences over the summer. This summer school just gave me a lot of insight about looking from a different perspective to a problem. So our project was about looking into the blue water footprint of a transboundary region in the United States. So we were team 3. So the team lead was Dr. Santosh Palmati. And the project was to estimate the blue water footprint of a reservoir in the transboundary US-Mexico region. This is a topic a little bit outside of my comfort zone, and I have learned a lot during the week of summer school about the issue of transboundary water. So let's go back and see what is transboundary water and what is the conflict about these transboundary waters. So any river basin, any water body that's shared between countries is considered as a transboundary water. So in the world, there are 286 river basins shared by 2 or more countries. And one of a few of the examples of these transboundary waters are Nile River, which the disputes between Ethiopia, Egypt, and Sudan over the Grand Ethiopian Renaissance Dam. And the other one is Indus River, which is shared between Pakistan and India, and they have a water sharing agreements between them. And the other one would be Helmand River, which is shared by Afghanistan and Iran, and they also have a water sharing agreement between them. And these challenges include conflicting the international interests of the countries. The climate change is one of the challenges facing these transboundary water bodies and rising water demands in these areas. So let's just see the locations of these river basins. These blue, dark blue areas and regions are those with the transboundary river basin. And as you can see, almost many countries and many regions in the world, they are dealing with this challenge in the water resources. And about 151 countries and about 2.8 billion people are sharing these water resources among them. So we can consider it as a main challenge in water resources management. And there are many factors that are worsening these transboundary challenges. And these factors, which are environmental, human, and agricultural water stresses, are just adding up to the risk of these transboundary conflicts. So, and based on these factors, few of these river basins and shared water resources have a higher risk of conflict. And US-Mexico border region is one of those high risk regions for transboundary water conflicts. So it's not that all the time there is a conflict of transboundary water. There are many good examples of a successful transboundary water management. One of these examples is Rhine River Basin in Europe. This river is shared between 9 countries, and it's managed through a coordinated agreements like the International Commission for the Protection of the Rhine. So these countries are working together to mitigate the pollution in the river and also promote the sustainable water use for these countries. So we, as you can see, collaborative framework can make sure that these transboundary water conflicts can be resolved. The background and motivation of doing our research in the region of US-Mexico border. So southwest of the United States, it's arid and semi-arid climate, which is facing water scarcity because all the climate change effects. So, and this basin is really rely on the water, on the snowpack from the Colorado River Basin. And there is also a rising water demand in that area because of different reasons, which I will just talk about that in the next slide. And because of this and this situation in that area, the US-Mexico region is also home to over 10 million people, in which most of them are Latinx communities. So why it's important to look into these transboundary reservoirs? So these reservoirs in transboundary regions are the main resource for agriculture, drinking water, and energy production. And these reservoirs are shared between different entities and one of these reservoir and basins in the US-Mexico border is Rio Grande River Basin, which provides water for over 10 million residents of that area. And climate change, population growth, and the change of cropping system and agriculture is making it worse to provide water for this region. As you can see in this map, you can see that area of Rio Grande Basin, which I have highlighted it, has the highest population intensity and density among the communities and regions in the border. So because of this transboundary water, US and Mexico just came up with a few treaties to share the water based on few features. So in 1944, they just established this first treaty between US and Mexico. So based on this treaty, the water was shared through Rio Grande River between US and Mexico. And it was like that US have to provide and delivers about 1 million acre feet of this water in Rio Grande and Colorado River to the Mexico, and Mexico have to deliver about 350,000 acre-feet annually from Rio Grande to U.S. soil. So this was the first treaty, and they have just revised the treaty over the years, and now there are 3 different treaties for that region, and each treaty was just trying to resolve the previous conflict over the previous treaty. So let's look at the Rio Grande. So this river is the main water provider for that region. And there has been tons of news about this river this past year. And most of the news were just focusing on the ability of delivering the water from Mexico to the US. So if that amount of water could not be returned and delivered to the US soil and US border, the communities and factories, industry around that area cannot survive. As you can see, because of the climate change, Mexico cannot deliver that amount of water into the US border. One of the main reservoir in Rio Grande River is Elephant Butte. So this reservoir is located in New Mexico, and it provides water for the downstream communities for agriculture, drinking water, for the industries downstream. And as you can see, it's been shrinking over the years because of the climate change and lack of snowpacks in the Colorado River Basin. And of course, if we are talking about transboundary water, we should consider the social aspect of this challenge. So shared water, shared lives. The Rio Grande and reservoirs like Elephant Butte support millions of people in that area, in the border region. And it's a key to regional livelihood, agriculture, and urban water supply for these people. And there are cultural and community impacts of this type of management and conflicts. So water scarcity disproportionately affects communities, which are mostly underrepresented in the area. And the shared resources foster collaboration, but can also ignite disputes among the countries. And population growth and urbanization can worsen the conflict, of course. And the rising demand for water due to increasing population in border can impact the management of these transboundary waters. And also there are environmental justice related to this type of management. So the research objective was to estimate the reservoir storage change using remote sensing data and machine learning to be able to know how much water is available in that reservoir to be distributed for different reasons. And we were trying to answer these 2 questions with doing this research. What are the factors influencing reservoir storage? And also, can leveraging available observed data help develop a generalized predictive model to estimate the storage volume? So from here, I think Nitesh can take over and talk about it. I'm just going to stop sharing, and Nitesh can share his screen.
Sure. Thanks, Mariam.
Yeah.
So I guess my screen is visible now.
Yeah, but it's not on presentation mode.
Sure. Give me a second. So
All you have to do is click the right where you just were, go back to, yeah, there you go. Perfect.
yeah, thank you, Mariam, for introducing the study and the problem. So as Mariam said, in this research, we'll be trying to answer uh, if we can use remote sensing data and machine learning, and also test two different scenarios where we have for US dams, we have field measurements, and also we do have a remote sensing data that's freely available. So we do wanted to experiment with both scenarios of using only remote sensing data and the available reservoir storage from Elephant Butte Reservoir to model or to predict the reservoir storage, to see how either field-based measurements or remote sensing data can be let's say remote sensing data can be replaced with field-based measurements, or which uh, kind of gives us a better accuracy on predicting the reservoir storage, which could have a lot of implication on what Mariam was talking about. So in this study, we kind of used reservoir storage data from Elephant Butte Reservoir, which is available in the reservoir database of US, and that's our testing data. And we used other variables such as reservoir surface area, which is extracted from Landsat images between 2002 and 2030, 2023. Yeah, I suppose it's like about 20 years of data. And yeah, it was from 1990. It's almost 30 years. Yeah. So we have had a modified normalized differential water index to extract reservoir surface area from the Landsat images, from Landsat 5, 7, and 8, available between 1990 and 2023. And we also use the precipitation data set, which can be seen here, which is one of our independent variables from the remote sensing data sets. And inflow and evaporations are our field-based data that is available from the reservoir database. And we also used air temperature data from the remote sensing mission. And we also use volumetric soil water that's available from GL DAS data. So we kind of proposed these two scenarios. We tested these two scenarios where we only used uh, remote sensing data sets, and scenario one is using all the data sets. So the purpose we used, or we tested these two scenarios, was to see if the remote sensing only model can predict as accurately as a model where we have all the data sets from both remote sensing and field-based measurements. And typically, we used 60, 20, and 20 partition for our machine learning model for training, validation, and testing. And we used two models for this problem, since we were working with time series. So we wanted to work with LSTM, which kinds of analysis time series and sequentially. And we also use random forest to test between these two models on how they kind of predict the reservoir storage, and to see which of these two models predict better. And we do have our model evaluation using mean square error and root mean square error values. So as I said in my previous workflow slide, so our target variable was the real-time storage, reservoir storage data. And on the bottom are the independent variables that we used, which are precipitation, soil moisture, temperature, inflow data, evaporation, and area. So these data sets were converted to their representative SI units before using it in the model. So as we know that random forest is a majority voting decision tree based algorithm. So in random forest, what we did is, in order to make the time series data sequential, so we kind of used partitioned the training, validation, testing. Like we gave the first initial 60% of the time steps for training, and then the later 20 for validation, and the later 20 for the testing. And long short-term memory, LSTM. So we wanted to also test if reoccurring neural networks, which kinds of analysis data sequentially, can better predict, because our problem is time series based. So we wanted to test both LSTM and random forest on their accuracy of predicting reservoir storage. So this is our results for the scenario 1, where we use both the field-based data and also in combination with remote sensing data that we get from the freely available missions. So on the left-hand side, you can see the time series, which is the blue is the observed time series of reservoir storage volume change, and while the red one is the predicted reservoir volume change by random forest using scenario 1. So one another thing is we tested both models on both scenarios to see which of two scenarios kinds of works better, or kinds of is standalone. And on the right-hand side, we have the feature importance from Guinea impurity of random forest, where we found that kind of evaporation stands out to be an important factor influencing the prediction of reservoir storage volume change in Elephant Butte, next to which the temperature and volumetric soil moisture, and then we have discharge. Yeah, most interestingly, kind of the remote sensing parameters kind of helped in predicting the reservoir storage volume change in most of the two scenarios with both LSTM and random forest. So this is our scenario 2. Let me just. This is our results from scenario 2. So we'll show the mean square error and root mean square error in the next coming slides. So when only using the remote sensing based data sets without using any field measurements, we kind of get that the temperature, which kinds of affects the evaporation physically, stands out as one of the most influencing factor contributing to the reservoir storage volume change. And you can see that both in scenario 1 and scenario 2 of random forest prediction, that the observed and the predicted time series are kind of have a similar pattern, and their correlation is almost like it has 80 to 90% of accuracy on pattern wise, while so yeah, I'll go on to talk about LSTM. So these are our root mean square error and mean absolute error values for both the scenarios from random forest model, where we can see that remote sensing based data kind of have a similar error range to that of dataset, which all the independent variables we used from the scenario 1. And from using the random forest model, we can see what we observed was that the remote sensing, I mean, only using the remote sensing data set can actually almost closely predict the reservoir storage volume change as equivalent to those of scenario 1, where we used both remote sensing based data sets and field based measurements. So the implication of this observation is that without so let's say if there is a reservoir that does not have much of a field-based measurements, then from this kind of observation, we kind of think, or we kind of see that remote sensing data set only can almost predict the reservoir storage volume change equivalent to that of using field-based measurements, and this can be useful for those dams or reservoirs that's around the world which doesn't have any field-based measurements or in situ measurements. Yeah, so that's kind of inference that we got from using random forest. And this is our results for scenario 1 from long short-term memory. So on the left-hand side, we have visualized the model loss, where you can see there's a sharp overlap after like 5 to 10 epochs. I mean, the data set is very it's kind of a single time series for every variables, including target variable and the independent variable. So yeah, we trained it with kind of 100 epochs, but then almost the training and validation data converge at uh, like 5 epoch. And on the right hand side, we have the prediction versus actual reservoir storage volume time series. And you can see that other than from the random forest based predictions, this looks kind of different, and it's kind of looks lagged, where the predicted is kind of lagged from the actual observations. And it's kind of interesting because LSTM is kind of a sequential deep learning model, where it kinds of analyzes the time series sequentially and is supposed to have better accuracy when using time series data, because it not only sees the particular time, but also it sequentially analyzes the time before and the time after data. So when we started working with LSTM and random forest, we thought that the long short-term memory algorithm would have much better prediction accuracy than random forest, but we found that it can be due to short time that we've been working on this project in the summer school, kind of 2 days. Maybe it can be due to hyperparameter tuning, or we know that the LSTM models kind of are data hungry, and it kinds of need a lot of data to have a better and good predictions. So that's one thing to take into account when looking into this results, because this is just a one-time series that is temporarily spread across these many years. So our scenario 2 for LSTM models with only remote sensing data set, we also kind of see the similar pattern, where there is kind of lagged prediction than to the actual reservoir storage time series from LSTM from our scenario 2. And these are our RMSE and mean absolute error values, which are kind of more than that of what we see from random forest model. And with LSTM, what we see is the model that has kind of all the data with field-based institute data and remote sensing data kind of have more RMSE than the remote sensing data. This is kind of interesting because using LSTM, this gives us a kind of an impression that using only remote sensing data is kind of enough to have a better prediction, which is kind of interesting for us from using LSTM. Yeah, so this is from the random forest. So I'll stop sharing from here to pass this to Mariam. So can you take from here, Mariam? I think you're muted.
Yeah, sure. Thank you, Nitesh.
Sure.
It was really nice. So let me share my my screen now. So why it's important to know all this information? This information of knowing how much water is available throughout the year can help to support policymakers in fair water allocation based on the treaties in the US and US-Mexico border. And knowing this information can help them to help the policymakers and water managers to inform strategies for climate resilience and drought adaptation in the area, and promote sustainable agriculture and water use in arid regions. And also, by doing this, we all know that many research have their ethics and limitation. And it's also true for this type of research that we've been doing during the summer school. So the ethics coming with this research was that we were using open source data to make the research more accessible for people. But the code and notebooks were just only accessible through the iGuide platform. So it was sort of an open access research, but also not. And that was something that we were just considering as an ethic for this research. And the limitation, the first one was the time. We were doing this research, as Nitesh said, in 2-3 days overall. And we came up with the idea, we found the resources, we discussed our approaches to do this, to answer this research question. And so this just time constraint can bring more challenges for this research. So one of the challenges and limitation of this research was not having several locations and several trials of the models to just compare their accuracy in different locations in the same region and with different data sets, with different machine learning models. So, and the other limitation was we haven't quantified the uncertainty with these models that we've used. So if we are going to use these results, we should be careful about these limitations. And just if someone wants to use this research, they need to have a really high expertise in GE, Python, deep learning, and machine learning. So this is another limitation of doing this type of research. And we had planned to just move forward from where we were just doing that research in summer school. So we want to test other machine learning models and see the results of the other machine learning methods. And we want to include the climate data with different sources and with different products to see if the result changes by using a different data set from a different resources. And we want to scale up the model of this estimation of the reservoir volume, and sort of if we can to just generalize the model to other reservoirs in the same basin or in the same region. And we are planning to share the research findings in the form of peer-reviewed articles and book chapters. So here is, we acknowledge the fundings that's been received and enabled us to do this research during the summer school. So we thank iGuide to providing this platform and opportunity for us. It was a great experience and learning moment for, I think, all of us. So, and this is our team and our team lead. And as you can see, we are from different institutions across the country. And that's the end of the presentation, I guess. And if you have any questions, we would be happy to answer.
Thank you, Marianne. Let's leave this up. Let's leave the slide up for a minute because it's so great for, thanks for putting together all the QR codes. Do they pretty much go to people's LinkedIn pages or? Yeah.
Yes, it's straight to their LinkedIn pages.
Excellent.
Thank you.
So anyone from the audience, please feel free to put a question into the chat for our group. Thanks for saving time for some questions. I was wondering if you could, I thought it was interesting, the observations you made about access in both ethics and limitations, where the data set is open access. I mean, technically, it's the iGuide platform is open to anyone, but in order to log into the platform, you need to have kind of, let's call it a specialized account, but it's free to get a specialized account. But more interestingly, you need to really have the knowledge of what to do, that advanced knowledge of what to do when you get to the platform, or what to do when you know, what do you do with a Jupyter notebook? So given those existing persistent types of limitations, especially with this kind of work, which has so many important implications for policy, what do you do about that? How do you communicate? How do you begin to communicate some of the experiences and knowledge that you've gained here to people who are on the ground, policy makers or people engaged in policy conversations?
That's a great question, because all the time we want to see the implications of our research in the field and see how it affects the people's lives. My research is far from a transboundary water, so I cannot see a direct result of this research. But maybe if Dr. Palmati is here, he can answer this question, because he's directly is working with these communities and this type of water management in the region. So I think he can give you a better answer for this question.
And Dr. Palmati, feel free to turn, if you'd like to. I don't mean to put you on the spot, but feel free to jump in. And if now is not the right time for you to make this unexpected jumping onto a Zoom, I'm kind of interested in general about the experience of the students with these working in this advanced technology field, and the experiences that you have at your respective universities in talking about making that research more accessible to others, whether they be policymakers or others, because it is it can get very specialized and very complicated and advanced very quickly, which is important to be able to do to gain the knowledge. But it's like, how do we get outside of just that deep technology area?
Can you hear me?
We can't hear you very well, and I'm sorry. I know that you hadn't expected to be put on the spot like this. No, your microphone's not working very well. don't worry about it. We know that you hadn't expected to be jumping in like this.
Yeah, maybe it's okay. I can share my experience
Yeah.
of being a student. So my work is in the extension framework. So, and I work with water quality and with farmers. So my research would just affect policymakers and farmer and stakeholders directly. So as someone in extension, you know, beside meeting with the farmers and the stakeholders in the different, you know, settings like workshops, just interviews, just one-on-one meetings, I usually try to prepare something for them, like a flyer, uh, because I'm just directly working with farmers and their stakeholders, and I just have some really general information of the findings for them, and I use those flyers when I'm meeting with them, so I can just point out to the result and just show them, okay, by doing this, you will see these effects in your water quality at the end. And the, you know, bigger picture of this type of practices that you are doing is that you just the mitigation of like dead zones in the Gulf of Mexico. And these are just the experiences I'm directly using in my field of study. And I think for even that's even true for this type of research. So if we know the findings, we can just share the findings in a really simple way in the meetings with the stakeholders, with the you know, policymakers and water managers, the different organizations who, you know, that manage the water in the area. So it can be just a click to think about something for them, and I hope that at the end of the road we can see some impact of this research. I don't know if that was an answer for your question.
No, I mean, very much. I think universities that have, not every university has an extension mandate, but that extension mandate is by design meant to bridge that the knowledge between the research into practitioners. And yeah, I think that any university, when your university has an extension mandate, and when you have opportunities within your particular department to be able to engage with those practices, I think that's very much a on the ground important example of how it actually has to happen. It doesn't, the structure might be there to facilitate those conversations, but it doesn't necessarily make it any easier to do that knowledge exchange. It's just that the expectation is there.
Yeah, that's true.
Yeah, there is a question in the chat from Mazda. Thanks for the question. That's a really interesting question. He's asking, I'll be reading out the question and answering it. Is your model able to predict the extreme climate conditions? So I guess the question is to ask if there is an extreme climate conditions, whether will our model help predict the reservoir storage volume gain during the extreme climate conditions or the loss of storage. I mean, that's, basically with our target variable and the independent variable, you know, machine learning or deep learning is basically a regression model, which is kind of the changes in each variable, even during the extreme climatic conditions, might have effect over the target variable that is water. I mean, the reservoir storage volume change that we are trying to predict. So I don't know how far we can kind of predict that exactly. I mean, how will be the changes? But I'm sure it can predict. But I'm not sure on what level of accuracy it can be predicted. And I mean, if you are talking, I mean, if you are talking about like kind of predicting extreme gain. I don't know, these climatic extremes are really kind of hard to predict, especially given that if there is past events that are given to the model to be, if the model already is trained on extreme conditions, then yeah, it can do well. Or I don't think yeah, we haven't looked into it, but it's a really important question to answer, given that this climatic extreme conditions that we have been seeing in the west and southwest of US, even in northeast this year, we do have some climatic extreme atmospheric rivers, which could potentially impact the reservoir storage. But it's kind of a gray area. We haven't experimented with any data, and yeah, in those 2 days of the summer school, it's kind of really hard for us. But it's an excellent question, and yeah, I mean, we would like to work on it in the future. But yeah, I'm far away from surface water research. I'm more into groundwater research and geodesy. So yeah, probably Santosh or our another group mate Kanak is in the chat. Probably he or Santosh might give a better reply. Thanks.
Thanks for responding to that. So we just mentioned that our summer school is a very brief, intense opportunity. It's really only 4.5 days altogether, unfortunately. And students work on these projects in different small teams, but it's necessarily limited by a number of factors to be able to take a project that can be looked at over just a few days. So it's a great opportunity for students to get introduced to some of these techniques, to work with interdisciplinary teams. We do have a summer school 2025 that's been scheduled that will also take place at the UCAR facility in Boulder, Colorado. The dates are August 4th through 8th, 2025, and soon, in the next month or so, you will see a call both for team projects and team leaders, and a call for the application opportunity will be opened up, I think, in January for students or early career faculty to apply to our 2025 summer school. Any other questions for this group? Please feel free to put them into the chat. In the meanwhile, I'm going to remind you about some other things coming on with our virtual consulting office session. I'm going to put this into the chat. We have 2 more sessions this semester, this calendar year. One is coming up next week, and it's an opportunity for people who don't know about it yet to learn about our current spatial AI challenge. I just put the link to that in the chat as well. This is currently underway. It's an opportunity to get some help developing your ideas, working in the AI world, working with data applications and models, or also we have a couple of open problems that should be able to be addressed, and you can learn about those there. To apply, you only need to submit an abstract for the AI challenge. You don't need to put everything together to begin. Just to submit an abstract for it, and those selected to participate we will work with you in over the course of January, February, March to develop your content more, and then use that iGuide platform that you heard referenced before. You're also going to see that we're going to start doing VCOs on our iGuide platform on a regular basis, just to help people understand how the system works, understand how to take advantage of a lot of the new functionality that has been added even since last year's summer school. So I encourage you to think about that VCO as well, learning about the platform. One final comment here: if you or colleagues or the faculty that you work with happen to be affiliated with a UCGIS member institution, which is about 50 universities out there, we have right now also underway what's called our Community Champions program, and I'll put the link for that there as well. The Community Champions program this year is connected to the AI challenge. The idea is that you would be a faculty member or a researcher or an advanced student who's already doing work with AI, who already has data, model, or applications, and would be able to work on those quickly together within the context of our platform and be able to have them on the platform so that when the rest of the AI challenge is going on, especially in February and March, you in fact would become part of the iGuide group that helps serve as mentors for the people participating in the challenge. So, and the challenge offers, the Community Champions program offers actually a $3,000 honorarium or that equivalent amount in a type of travel award if for some reason you are under a visa status that wouldn't allow you to receive an honorarium. So again, that's part of the Community Champions program, is for people who were affiliated with UCGIS member institutions. Somewhere in there, there's a whole link to the different schools, universities, the 50 or so universities that are affiliated with UCGIS. So take a look at that if it's not something you're familiar with. They both have upcoming deadlines, but you only really need to put an abstract together by these upcoming December deadlines. So if you're not yet familiar with these programs, please consider applying, consider forward these around, let all of your colleagues know about these. Okay, so any last call for questions about this research here? And I'm sorry, Dr. Palmade, that we weren't able to get your audio to work, but I appreciate very much, we appreciate all the work you did guiding this team and getting them to this point over those very brief, intense number of days. So if there aren't more questions, we'll wrap it up. Thanks everyone for your attention. This recording will be processed and it will be available on the iGuide website with our at our VCO collection after it has been done. Yes, congratulations to Miriam and Nitesh, but also everyone who participated on this Team 3 and all of the iGuide summer school teams for getting so much accomplished in such a short time and for really presenting all of the work that you did. Again, these two presenters are part of this larger team. We're glad we could highlight the others here with their LinkedIn, links to their LinkedIns as well. It's a big team effort. Thanks to everyone for participating, and take care. And I hope the end of everyone's semester wraps up smoothly. I know this is a super busy time of the year.
Thank you. Thank you.
Thanks, everyone.
Thank you.
Yep. Bye-bye.
Bye.